what you're putting in. All your hopes and efforts are all in vain. Who will pick you up when you've lost everything? Does it all become for granted with a wedding ring? Oh, there must be more. There must be another way. There must be conscious, different things in different ways. There must be love. There must be a reason, and a little bit of faith has got to come my way. I was just a little girl when my mama used to say, ooh, happiness requires work every day. Oh, and if that someone makes you smile and leaves you with a scar, don't let them tell you what you feel or who you are. Oh, there must be more. There must be another way. There must be conscious, different things in different ways. There must be love. There must be a reason, and a little bit of faith has got to come my way. I gave it all to you for too There must be more. There must be another way. There must be conscious, different things in different ways. There must be more to the reason why we do it all for love. There must be more for a reason, and a little bit of faith has got to come my way. Has got to come my Has got to come my way. Do you ever feel you don't get out what you're putting in? All your hopes and efforts are all in vain. Who will pick you up when you've lost everything? Does it all become for granted with a wedding ring? Oh, there must be more. There must be another way. There must be conscious, different things
And welcome everybody. It's great to have you here. I have been doing some tweaking and tuning here in my studio here in Las Vegas, and I'm having so much fun. Oh my gosh, with various scenes and changing back and forth. Hey, it's great to have you here. It is Saturday. It is Subnet Saturday to be specific, and we have some objectives regarding what we're going to cover today. And if you haven't already done so, I would encourage you, if you're new to IP and new to networking, please check out the playlist on Subnet Saturday. It's called Subnet Saturday, so you can get caught up and make sure you're right there along with us. So they're on a playlist, so you can go back and look at them anytime you want. Okay, our objectives for this session today is to focus on block size. Now, for some of you, block size, like, oh yeah, I totally get it. And for others, it's like, block size? I don't know what that is. And that's perfect, because that's what we're going to talk about in this video. So I have my notes, and I went through all the details I wanted to cover today so I could be nice and concise. And also, we'll do some hands-on and some demonstration and make sure you get it and can use it. So regarding block size, here are our objectives. I want us to understand, number one, three basic things. Number one, what it is. Number two, how to figure out the value of it. So we understand what it is, how to figure out the value of a block size. And then third, why do we care and how can we use it? The block size to me is one of those things that's come so useful so many times, and you'll really appreciate it once you start getting into IP and subnetting. So that's our goal. Three things: what it is, how to calculate it, and then third, how to go ahead and use it to make your lives better. So to start off, I've got a whiteboard. Let me share that with you. And let me bring this up right here. And fantastic. Okay, so let me just verify this. All right, wonderful, wonderful, wonderful. So let's imagine that we have a computer with this IP address, 10.0.12.1. So that's the 32-bit IP address represented in dotted decimal, and this is the mask. And I thought to myself, it'd be pretty cool if we could actually maybe verify that. So let's just go take a look at a device in our topology that has an IP address like that, and I've got one right here. There's a little router, if I can log into him here. And this router, which is router 1, if we do a show IP interface brief, that shows us a nice, concise view of the interfaces, and it includes some cool details, including what is the status of those interfaces. Are they up, or are they administratively down, or are they down because there's a layer 2 issue present with them? And then also over here, because we had the keyword IP, is showing us the IP information. So this shows us the IP addresses, but it does not show us the mask. So what in the world are we going to do if it doesn't show us the mask? Well, we have to issue a different command. We could do a show of the running config, or we could do a show IP interface for a specific interface, and that will show us both the IP address and the mask and some of the details about that interface. So let's go ahead and do that let's pick this interface right here. So gig 1/0 has the IP address 10.0.12.1, and let's ask it for more information about that. So we'll do a show IP interface for gig 1/0 and press enter. And among other things, and I'll scroll up just a little bit. So here's the command we issued, show IP interface for gig 1/0. And the point I wanted to focus on here was that here is the IP address, 10.0.12.1, and the mask. So I'd like to take a look at that mask for a moment and just talk about that. Now, we've had this discussion in other Subnet Saturdays, and so we've talked about the mask and what a /24 means. And what a /24 means is this. Make sure it's right side up. So this is a 24-bit mask. It means that the first 24 bits of the mask are all on, pop, 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 24 times, and then they stop, and then they turn to zeros, and that's the dividing line. So everywhere there's a 1 in the mask, it represents the corresponding bit in the IP address that this mask is associated with is representing a street name, like a network name. And then everything where there's a 0 in the mask, those bits in the customer's IP address or the host address are the host address. So that's how that works, and this is a visual representation of this mask right there. All right. So this mask of /24, let me get my pen here. This mask of /24, it could be represented in dotted decimal as 255.255.255.0. So no mystery there. This means that the first 3 numbers of the IP address is the network. So we could say this computer is on network 10.0.12 with a/24. And another cool thing is we could prove, and its host address is .1. And we can also prove that by just asking the router, hey, what streets do you believe you're living on? And the way you ask a router that question, what streets do you believe you're living on, is by doing the command show IP route. And that will show us the networks that this router believes it can reach, including its directly connected networks. So if we do a show IP route, and I'm also going to add on the keyword connected. That way it won't show us OSPF routes, or it won't show us EIGRP routes or BGP routes. It'll just show us routes that are directly connected. So the one we're looking for is this bad boy right there. So this router believes it's connected to the 10.0.12 network with the 24-bit mask because it has an IP address on that interface of 10.0.12. something. We have .1 in our case. And so that's why it believes it is directly connected to that network. So going back to our discussion of block size, now that we have an example to work with, let's do this. Let me share with you the secret of the block size. And let me go ahead and bring up another layer to do this so we can erase it later if we need to. All right. And let me use a slightly different color. Let's take example number 1. Oh, that's a terrible color. Let's use that. Let's use, how's that look? Wow, those are all terrible colors. Hold on a second. Let me bring up a new layer, see if that helps. I want to be able to read it. I mean, if we're going to write something, I want to be able to read it. Look at that. Hold on one moment here. Oh, I will punt, and I will use a different tool because that's what we're going to do. Okay, so we'll use a different tool. All right, so for this example right here, the 10.0.12.1, that's the IP address on that interface of that router, and here is the mask. And the block size can be calculated based on the least significant bit value of the mask. Now, let's break that down. Let's take a look at the least. I'm talking about the mask. Let me bring up my ruler again here. In this mask, the high order bits, the ones that have the most value, 128, then 64, then 32, and so forth, over here on this side. And as we go down, those values go less and less. So the first bit has a value of 128, then 64, then 32, then 16, etc. And that happens again and again with each octet. So when we take a look at the least significant bit of the mask, it's so simple. So simple. All it means is you go all the way down in the mask till the bit stop, which in this case is right here, and you look at the value of that last bit that's on. The value of the least significant bit, or the last bit that's on, that's what we're after here. That's it. That's the block size. It's the value of the last bit in the mask. What is its value? So let's take a look. So here in this this mask, if we wanted to find out the value of that last bit, we would take that 255. So I'm going to take this example down here, and we're focusing on this third octet. So that's the third octet. So if we wanted to break that out, it would be 1, 2, 4, 8, 16, 32. Oh, I'm out of room. Hold on. Bump, 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 bump. Give myself a little more room. 1, 2, 4, 8, 16, 32, 64, 128. So from our previous discussions, we're all familiar with those are the values, the decimal values of each of the positions in an octet of data. So if we're looking at this third number here, I'll say the second octet, the second number, it goes that way, and this is the beginning of the third number, and then over here we have a period, and the third number is there, and the fourth number will go off to the right. So if we want to take a look at 255 in binary to find out what the least significant bit value is, it'd be all ones. I'm just going to put 255. 255 for the first octet is all ones. 255 for the second octet is all ones. And now for this third octet, which we're focusing on right here, it would be, for 255, it would be 1, 1, 1, 1, 1, 1, 1, 1. That is the binary value of that decimal number, which we've talked about in previous sessions. Then the rest would be all zeros going to the right. So our question here is, the block size is the last bit that's on. And what I would have us do is I'm going to have us go ahead and put a literal, like a rectangle or a block around that. And that is the block size. So the block size is the value of that last bit that's on. So my question for you is, what is the value of that 1 bit in this position right here? So if you want to chat that in, I would be obliged. What is the value? So that bit, this is the last bit of the mask. So another term for that is the least significant bit out of all the bits that are on in the mask. This is the least significant bit. What is the value of that bit? And I will wait for a moment. I've got there's a teeny bit of a lag between the time that I record this and the time it goes out, maybe 15 to 20 seconds. So I appreciate your patience. Yeah, great. Gus and Bhaskar, I don't want to say that incorrectly. Fantastic. It's a value of 1. So the block size, based on this mask, the last bit that's on in that mask has a block size or a value of 1. Just 1. That's perfect. Great. Block size. The value of the last bit. Now, when we have nice, clean octet boundaries like that, that last bit is going to be in this position. It's always going to be a 1. However, I'd like to take a look at another example. And again, thanks for all the feedback pouring in. You guys, you are all rocking. Fantastic. Let's take a look at another example. But this time, let's take a look at an IP address of 10.67.83.1 with this mask of 255.255.224.0. And to do that, let's go ahead and bring some reality into the situation by actually going to an interface that has that IP address. And if we don't have one, we can create one. I had a question recently about loopback interfaces, and this is a great time we can elaborate on that. Imagine that you have a router with 4 physical interfaces. So it can be connected to 4 different networks. We have 4 interfaces. We bring them up. We configure IP addresses on each of them. And so each of those interfaces is logically connected to a street, like a network, a different street for each one. Now, if we create a loopback interface, it doesn't have any way to connect with, it's not physical. It's just like a holding place in the router. So we can say interface loopback 99 or interface loopback 10 million. It's just a number, and poof, it's created out of thin air. Like, why? And that's a good question. So the question that Ardent Defender was asking in the chats on the last video was, okay, so I'm not clear on this loopback interface. Why would you ever use it? And one of the reasons to use it would be this. Let me show you a topology. And then we'll go ahead and we'll create one and we'll demonstrate it. So let's go ahead and let me hide this. And let's imagine, let me clear that off. Let's imagine that we're PC4. So this is Bob. So Bob is sitting here at PC4, and Bob wants to do a ping periodically to make sure that he can, that router 1 is working. He wants to make sure that he can get over to PC1. This is good friend Lois over here. And so he has 2 possible paths. This is the preferred path if we're running OSPF because it's going to have less of a cost. So path A is one option, and path B would be another option in case path A goes away. So let's imagine Bob says, you know what, I want to just do some periodic tests to make sure that I have reachability over to Lois. And so what Bob could do is he could do a ping to this IP address on the router. So router 1 gig 1/0 that we just looked at has the IP address of 10.0.1, and this interface gig 2/0 has an IP address of 10.0. And that's going to be the 13 network, 13.1, and those are both using a 24-bit mask. So Bob decides, I'm going to just set up a routine, and I'm going to ping from R4 over to R1 gig 1/0, and that way I can verify that my network path is working. However, what happens if gig 1/0 goes down? Well, Bob's ping to that IP address is not going to work because the interface is down. So what's to be done? Well, instead of pinging a physical interface, what we could do is Bob's R1 could create a loopback interface. Think of it like just a logical layer 3 interface that doesn't really go anywhere. Create that on R1, and let's say it's loopback 777. So we create the loopback interface and we give it the IP address of, 10.0.77.1 or some other number, and we give it a mask, fine. We set up that IP address, and then we advertise that network in OSPF so it's reachable. And then, regardless of this one interface going down, if there's still another interface that is still forwarding traffic, Bob can now try pinging against that loopback address. And if one interface goes down, that's not the IP address we're pinging. We still have connectivity, and we still have access for testing connectivity across the network. So that's one example of what a loopback address interface is. It's just made up. It doesn't have any real connectivity, and unless a router advertises that route, that network, no one else other than that local router will be able to go ahead and reach it. So in this topology here, let me go ahead and clear this off. On this router, I propose that we create a loopback interface. And we'll create one for the purpose of this next example of finding the least significant bit. So the IP address, let's see, is going to be 10.67.83.1 with a mask of 255.255.224. Let me verify that real quick. Let me clear that and bring this back up. And I just want to verify I'm going to the right address. Yeah. So this bad boy right here, 10.67.83.1, nobody owns that IP address at the moment. I mean, there's not a single device on the network that has that, but we could create a loopback. Let's create loopback 777, and we'll assign it the IP address 10.67.83.1. We'll use this mask, and then we'll go ahead and identify based on this mask what is the least significant bit value of that mask. So we'll do those in order. And that way I can answer the question regarding loopback addresses and also address the block size at the same time. It's a 2-for-1 deal. All right, so let's go ahead and do it. Let me go ahead and clear that off. And let's go back to our interface. And it's right here. So here on R1, if we do a show IP interface brief, you'll notice I have I've got 3 physical interfaces right here. That's fantastic. They have IP addresses on them. I've got 1 loopback interface. And for me, the reason I use this loopback interface of 0 with a 11111 address is for my router ID in OSPF. That's the real reason. So in OSPF, when OSPF first comes up, there's 3 ways that can determine what the router ID is. The first way is you just configure it, router OSPF1 or whatever the process ID is, and you specify router-ID. This is the router ID. Done. If that hasn't been done, the next choice that the OSPF router will do when it first comes up, he'll say, okay, the router ID isn't configured, but I have a loopback with an IP address, and because the way they wrote OSPF for Cisco, I'm just going to take the loopback interface that has the highest IP. So if I have 10 loopbacks, I'll take the one that has the highest IP address, and I'll use that as my router ID. And if there's no loopbacks configured, it then defaults to the third option, which is just grab the highest IP address on any other non-loopback interface, which means like a real interface. And that's how it works. All right, so getting back to this, let's go ahead and create loopback 777. So config T, interface, loopback. And you notice we have quite a range of numbers to play with here. So we'll do 777 based on our plan. And the moment we do that, press enter. Check this out. Do show IP OSPF interface brief. And there's that loopback interface. Now it exists. It came up by default because that's what loopbacks do on this version of iOS. And now we just can assign it an IP address. So we'll give it the IP address with the IP address command of 10.67.83.1. Was that our IP address? Let me just take a peek at my notes real quick. 10.67.83.1, yep. And the mask, you can bring that back up. Hold on one second. And the mask is going to be 255.255.2, my brain, 224.0. All right, so basically what that means is that the first 8 bits of this number 10 is the network. This 255 means that the second number in the corresponding IP address, the 67 in this case, is the network address. And the 224 means that a certain quantity of this third number, this third octet, is representing the network. And so 224 boils down to 3 bits from that third octet. And we could determine that. In fact, let's just do it right here with some easy math. And let me bring up a pen. And here's my pen. And let's go ahead and do this. So if we are focusing on this third octet, first thing we're going to do is, if we're going to convert that to binary, we would just go ahead and do the powers of 2. 1, 2, 4, 8, 16, 32, 64, 128. So far, so great. So I'm going to put some decimals in, or point decimals in there just to make sure we're focusing on the right octet. So this is the first octet, second octet, third octet, fourth octet. So I'll mark that here as well. So second goes that way. This is the beginning of the third octet. And then at this period, this is the third octet that we're focusing on, and going to the right would be the fourth octet. All right, so if we want to take 224, if we're trying to figure out what the least significant bit of the mask is, we need to know where it falls. So if we do 224, in one of our sessions, we played a game called Does This Go Into? And we could do that here. We did 128, does that go into 224? Yes, it does. Does the remainder go into the remainder, or does the 64 go into the remainder? Yes, it does. And does 32 go into the remainder? Yes, it does. And it's going to look like this. So I'll save that discussion for how to do binary to decimal and decimal to binary for those videos which already have it in it. So far, so good. And then basically this is our dividing line right here, where everything to the left is the network, including the first 2 octets, and everything over here to the right would be available for host addressing. All right, so our goal here is, what is the value of the least significant bit of the mask? And I will put this in red. So what we're going to do is we're going to take there's 8 bits here that are on first octet, there's 8 bits here that are on. In the third octet we have 1, 2, 3. This bad boy right there is the least significant bit of the mask that has an on bit. That's it. So if we put a block around that, which is not a bad way to remember that this is the block size. My question for you now, which I would love you to chat in, is what is the value of that least significant bit of this mask that we've just configured for this interface on the router, the Loopback 777? What is the value of that least significant bit? Go ahead and type that in. And as you do, I just want to reinforce that this is your block size. So it's the same process as we did with the previous example. We're taking the least significant bit. That's the last bit to the far right that's on, and we are identifying the value in that position. So as the answers are pouring in 32, 32, 32, I couldn't be more tickled. So 32 is the block size based on this mask, and it's always based on the mask, by the way. It doesn't matter what the IP address is. All we're looking for is the last bit that's on in the mask. Wherever that shows up, that is going to be, the value of that bit is going to be our block size. Let's do one more example. And again, I appreciate the answers pouring in. You guys are great. Let's do one more example to confirm that we've got this down regarding the least significant bit of the mask, regarding the bits that are on in the mask. And so let's go ahead and do that. We'll clear the screen and let's go back to our example. And here we have example number 3. So we have an interface 10.67.83.1 with a /14. Oh no, Keith. Oh no, what are we going to do? Well, here's what I propose we do. Let's put this IP address on our router, and then let's go ahead and do the calculation for what is the least significant bit value in the mask with a 14-bit mask. So I guess actually before we go there, because this would be good, before we go to the interface, Cisco won't well, depends on what you're running, but most Cisco routers are not going to allow you to do a /14 when you're doing IP address. They want a dotted decimal mask. That's how you input it. So let's calculate what 14 is as far as dotted decimal for a mask, and then we'll go ahead and continue the calculation. So if we're looking at 14, here's how I read 14. I see the first octet is 11111111. That's 8 bits on for the first number, period. And then the next number, which is the second octet, is going to have 8. Look at this. I think you'll enjoy this. All I'm going to do is just start at 8 and go 9, 10, and add more. So 9, 10, 11, 12, 13, 14, and then complete the 8 positions for that octet. And literally, I'm just counting them out visually, number-wise. So if the mask is 14 bits, it's 14 bits. So 8 plus 1, 2, 3, 4, 5, 6 more. Based on my high math here, that's a 14-bit mask right there. And then this would be the third octet, and that would be all zeros because the mask is not taking any more bits for networking. And then the fourth octet would be all zeros. And so the dividing line, which is always a good idea to put in, the dividing line between which bits are being used for networking, for the network address like a street, and which bits are being used for host address is right here. That's the dividing. That hasn't, and that part has not changed since our very first or second session here with Subnet Saturday. The mask is responsible for identifying the dividing line, and it does so by bits on, are all network, and then when the bits go 0, 0, 0, 0, those corresponding bits from the customer's IP address are all going to be used as host addressing, like a house number on a street. All right, so our goal here is the block size, and let's because we're right here, let's do the calculation. So focusing on just this second octet, I'll go ahead and maybe use a slightly different color for some variety here, and let's use light blue. There we go. So just this second octet, if we broke it out, 1, 2, 4, 8, 16, 32, 64, 128, great. There's our powers of 2. And if we took these bits, so that's on, these first 4 are on. Also, just for learning, I just add a little visual space here between nibbles. Actually, that's what that, 8 bits make up a byte. And so often 1 byte of data, when we're talking about IP version 4 addresses, we'll call them bytes or octets. Octets meaning we have 8 of something. Like an octopus, 8 legs, or 8 whatever those things are. So if we call a byte an octet, or if we call a number in dotted decimal an octet, that we're just referring to the 8 bits behind it. So half of an octet is a nibble. I think this actual spelling is like NYBBLE or something cute like that. And so when I teach, I often put a little teeny space between the first nibble and the second nibble in the octet, just for learning purposes. And that way it's not just a dyslexia reading competition of like, oh, where? So just as a convenience, I add the space. The routers and the switches and the networking devices are not so kind. They're just going to use dotted decimal or slash notation. But I'm adding the space just for making it easier. All right, so first 4 bits on plus these 2 bits. So that's this one. And then these last 2 bits are off right here. So we can put in our dividing line, which I love to do, and maybe you will too, right there. That dividing line says everything to this side is going to be used in the customer's IP address for network addressing, like a street name, and everything to the right is going to be used for host addressing, like a house number on a specific street. And then going back to our block size game, you take the last bit. So you start, on the far left, going this way, stopping right here at the very last bit that's on, and you basically circle the value of that. So we're going to block. And by drawing a block, it might help you remember that that's the block size. So in this case, what is the block size? If a customer has this mask of /14, which equates to 255 dot, and that would be 252.0.0. My question is, what would the block size be for that mask? Go ahead and type that in. What would the block size be? I'm experimenting with a lot of different things, by the way, including higher res for these live streams, which is what's happening with this. This is my first one at 1920 by 1080. So hopefully it's enjoyable to watch, and I'll be tuning it as I go. All right, so I'm getting a lot. Wow, everybody's saying 4, 4, 4, 4, 4. You're so right. Knocked it, bam, out of the park. The block size is 4. So my objectives for you and I in this session and in this stream was to make sure that we understand, first of all, what is the block size? So let's just make sure we're clear on that together. The block size is the value of the last bit that's on in the mask. That's what it is. How do you find it? you could put that part of the mask in binary, line it up against the power, the 1248, and just block it off. That last bit that's on, just put a square around that value, and that's it. And you've done it in these 3 examples. So these 3 examples included a 24-bit mask. Let me clear that off. They included a 24-bit mask where the block size was 1. They included this 255, 255, 224, which is a 19-bit mask, and the block size there was 32 based on the value of that last bit that was on. And now here in the 14, based on the last bit that was on in the mask, the block size you're telling me is a block size of 14 of, excuse me, let me make sure I get 14 right, of 4. Let me back that up. I was in the wrong bit position. Bonk, boink, easy to do. A block size of 4. Okay, great. So we've accomplished a couple goals. Number 1, we understand what a block size is. It's the value of the last bit that's on. Fantastic. 2, we've identified how to calculate it, and not just calculate it, but also, based on a nice clean octet boundary like a 255, great, or a 224, which is not on a clean boundary because we're splitting some bits in that third octet, or if it's given it to us in CIDR notation. Sometimes that's referred to as CIDR, classless interdomain routing. But so if you see a /14, it just means 14 contiguous bits in the mask, and we have identified how to do it there as well. So great. I'm confident that if you've been with me through Subnet Sundays so far, decimal to binary, binary to decimal, the purpose of the mask, all those good things, and now we've identified how to calculate the block size, I would like to share with you why this block size thing rocks and how it's going to save you a boatload of time. Let's do that right now. All right, so let me go to my notes here. Let's take an IP address like this one, 10.0.0. Actually, this is a network address, 10.0.0/29. And let's say that a customer had an IP address, and the IP address was 10.0.0.11, and they were also using a 29-bit mask. So one of the benefits of the block size is you can calculate very easily what the network ranges are. Like, for example, if we were doing custom subnetting, and we'll get into the details of all that, but if we were doing custom subnetting, it'd be important to know, okay, here's my first network, like my first street, and what is my next street, and the next street after that. So the benefit, let's talk about the reason for custom subnetting. If we have a 10 network, like a private network, and it has an 8-bit mask, we can support millions of possible hosts on that network. It doesn't make sense to have just one logical layer 3 network with 1,000 devices on it. It'd be one VLAN, one broadcast domain, every broadcast from every other device. It'd have to be seen by everybody else. It's a nightmare. Also for security, we may have some groups in our company that maybe one group is engineers. We have a group for research and development. We have a group for human resources. And maybe we want to keep them in their own VLANs, and we need separate logical networks for each one of them. So the process of subnetting is like taking a huge street and chopping it up into substreets, different logical. So maybe we had Elm Street as a huge street, and we say, you know what, we don't want to put all the hosts on that one big street called Elm Street. Let's take that one big street and let's chop it up into logical smaller streets, like Elm Cove, and then a different street, a different subject, Elm Way, and Elm Avenue, and other creative ways of taking one larger network and chopping it up into smaller networks. And so that's where this is going, by the way. After we understand the binary and what the mask does, that's where this journey in the world of subnetting is going, is being able to pretty darn quickly, by the time we're done, being able to take a big network, like a big street, and chop it up and make logical smaller streets out of it. That's exactly the analogy of subnetting. And they call it custom subnetting because, if you have a 10 network and that's the major network, and you're chopping it up into smaller networks based on your needs, custom. So custom subnetting, or subnetting, or variable length subnetting, where some networks are 20 bits and some networks are 21 bits and some networks are 22 bits, etc. It's all the same game, just repeated over and over again. So if we have the block size in mind, here's how it can help us identify what the actual substrates would be if we're doing subnetting. So this is just one value that subnetting, that the block size brings to the table. Okay, so let's first of all calculate what is the block size for this. What is the block size for a /29? And let's do the math. So I know that the first in dotted decimal would be 255 for the mask, and this one would be 255. So that's a total of 16 bits. We're going for 29. The third octet would be 255. So that'd be a total of 24 so far. And then we would need in binary, I'm going to do the last one down here in binary. So to get to 29, we need 25, 26, 27, 28, 29, and then the last 3 bits would be off. So this is the 4th octet that we're expanding here. I'll put a little decoder there. So this is the 3rd octet to the left, 4th octet to the right, and a /29 means this. So if we were to do this in dotted decimal, it'd be 128 plus 64 plus 32 plus 16, and I'll write these out here. 1, 2, maybe do a different color. And let's use this. 1, 2, 4, 8, 16, 32, 64, 128. All right, so if we were to find out the equivalent, the binary to decimal equivalent of this, it would be 128 plus 64 plus 32 plus 16 plus 8 plus 4. Oh, sorry, that bit's not on. So I'm going to draw my dividing line. I'm also, while I'm here, going to go ahead and circle the block size, because that's the value of that position for the least significant bit is 8. So I'm going to say block size equals 8. We'll hang on to that for just a moment. But the value of that mask would be 128 plus 64 plus 32 plus 16 plus 8, which I think would be like, what, 248? And we could do that the long way, too. So, yeah, that is 248. So 64 plus 30, 64, 128 plus 64 plus 32 plus 16 plus 8 is 248. So when we put an IP address for the client, let's say we do 10.0.0.1, or let's actually do 10.0.0.11 like this. So we put the IP address of 10.0.0.11, and we put this mask in 255, 255, 255, 248, that's a valid IP address on a network. Now, the question would be, how is that block size going to help us in calculating what our subnets are going to be? And let me start over here in a slightly different color. And this will just be an intro to the concept, but it's just an example of why block size matters. So let's say we have 10.0.0.0 as our network, and we have a /29. The block size is 8 for this mask. And if everybody agrees with that, that's fantastic, because that's exactly what it is. Just like we calculated the block size for this mask and this mask and this mask, for a /29, the block size in that 4th octet is an 8. So if we have the network 10 over here, check this out. All we're going to do to find out the next network is we're going to add block size. What do you mean, Keith, add the block size? Well, the block size is 8, and the next network is going to be 10.0.0.8. We're in that last 4th octet here, /29. And if we want to find out what the next substrate is, like Elm Court and Elm Way and our additional substrates with this mask, the next one would be 10.0.0. And we would add 8 again, which would be 16. And then I'm going to do one more, because we're not doubling it. We're simply adding the block size each time. The next network would be 10.0.0. And 16 plus 8 is 24. And that would also have a /29-bit mask. So the cool thing about block size is that once you have a block size identified, you can go ahead and start adding that block size value every time you want to identify your next subnet, your next subnet, your next subnet. That's pretty handy. I'll tell you another benefit too, and I'll put this in a slightly different color. Let me go ahead and get, let me use white, that'll work. Let's imagine we have a client like this, 10.0.0.11. My question is, how do we know which of these subnets it's on? So sometimes this is called subnet 0, and this could be our first subnet 1, subnet 2, subnet 3. I don't like calling the first one subnet 0 because it's not really it's the first network, but they call it subnet 0. In any event, if you ever see subnet 0 being mentioned, like, okay, subnet 0, they're talking about the first network when you're doing custom subnetting. So if we have these 4 different networks, my question is, I'm going to label these. Let me take off that. I'm going to do A, B, C, and D because that'll be better. Network A, Network B, Network C, Network D. If we saw this IP address, and what I think we should do is, let's actually do it. 10.0.0.11 with the 29-bit mask. Let's go to our router interface and actually put it on. I wish there was some way we could, I don't know, make up an IP address for an interface without having to use a physical interface. We can. We'll create another loopback. Interface loopback. And let's go ahead and call this 6783, just for fun. So there's our loopback interface. It should come up, bada bing, bada boom, and we'll give it the IP address of 10.0.0.11 with that mask of 29 bits, which is 255.255.255.248. And that is correct. All right. All right, so it's done. If we do show IP interface brief. Cool. There it is in all of its glory. So Loopback 6783 has the IP address of 10.0.0.11 with a 29-bit mask. And my question is, which of these networks right here, as I bring that layer back up, which of these networks is that IP address on? Is it on network A or B or C or D? And one of the benefits of doing block size and actually identifying these is we have a range. Look at this. This is pretty handy, and we'll have more practice with this as we continue. But if we have the 10.0.0 network and we know that the next network is .8, that means that the range for the host addresses in this network A would be like starting with 1, and we can't go past 8 because that's the next network. So it'd be like 1 through 7. And the actual last IP address is reserved as a broadcast address. And we'll talk about that more later. But can you see here that this network 10.0.0.0 with this last 29-bit mask, if the next network is .8, we can't go any higher than .8 for the range. And that same logic continues here. So on network B, 10.0.0.8, that network, the range for those hosts would be 9 through, and the next subnet is 16, so it'd be 15 is the highest possible IP address. And again, the last one is reserved as a broadcast. And then if we take a look at the 16 network, the first IP address would be 17 through, and the next network is 24, so it'd be through 23. So going back to this interface right here, the Loopback 6783 that we made with the IP address of 10.0.0.11 with the 29-bit mask, my question for you right now that I'd love you to chat in is, which of these 4 networks is this client currently connected to? What's the street name? Is it 10.0.0.0? Is it 10.0.0.8? Is it 10.0.0.16? Is it 10.0.0.24? Which represent A, B, C, D respectively. And that's really handy because a lot of times we'll be working with an IP address or see a client. It'll have an IP address and it's not obvious to the naked eye which street this customer's on. But by knowing the block size, you can quickly jot out the subnets. You take the first network, add the block size, add the block size, add the block size, and then you calculate the ranges based on where the next one starts, and you're good to go. Wow. Holy schnikers. There's just a ton of people saying answer B. You'd be spot on. And that's just one of the benefits of the block size, is that we can take that block size and calculate the subnets and just say, oh, here's the range because this one starts here and boop, 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 calculate the ranges and boom. So you're telling me based on these 4 networks that we calculated with the block size based on the mask that this customer, this interface 6783 is directly connected to network 10.0.0.8 even though its last octet is 11. I think we should prove it, and it's pretty easy to do. Check this out. This is super fun. I'm going to go ahead and hide that for a moment. Let's go back to our interface. And here's what we're going to do. Show IP interface for Loopback 6783. I just want to confirm the IP address. So it's 10.0.0.11 with a 29-bit mask. That means the block size is 8. That means each network is going to be an increment of 8, and we calculate the ranges. And now let's do a do show IP route, and I'm going to say connected, because the router here's the thing about the loopbacks. The router thinks, oh yeah, I'm connected to that network. Now nobody else knows about that network except for that local router, unless he advertises it inside of a routing protocol like OSPF, and then he can share that information with others. But by default, he's the only guy who knows about it. So we'll do a show IP route connected to show us just the directly connected routes. And what I'm hoping for is that guy, 10.0.0.8. Is that what we thought? Hold on a second. Let me bring that back. So answer B, 10.0.0.8. Look at that. That's the network. It's not just like theory. That's literally the network that client is connected to. 10.0.0.8 with a 29-bit mask. Wow. Block size. Pretty cool. You want to know something else that's pretty cool? This is also very, very cool. I'm going to erase our other work there and start fresh. If we know that we have a slash, let me change the colors. If we have a 29-bit mask, like we have right here, and we already calculated that the block size is a block size of 8. And I'll put a block around that. So our block size is 8. If we had to do a wildcard mask for 10.0.0.8, so that's the network with a slash 29. Oh, this is kind of funky because the last octet is 8 also. But based on the block size, if we want to do a wildcard mask, wildcard masks, they are block size -1. So that means if we were doing OSPF and we wanted to include this interface in OSPF or that network, we could do a network statement of router OSPF. I'll put this in a different color. Router OSPF process ID, and then a network statement of that network, which is 10.0.0.8. And then for our wildcard mask, it'd be for all the first 3 octets, it'd be 0.0.0. But for that last octet, in that last octet where the wildcard mask is an 8, -1 is 7. So that's another very, very quick way of calculating wildcard masks. Is you can take in decimal, you can take the decimal number, subtract the actual mask that's being used. That works, but it's also taking the wildcard, the block, and still be subtracting 1. So if we were to do this, we could include this interface and this network, Loopback 6783, into OSPF. And I think we had to go ahead and try that to verify it works. Just one other example of how the block size could be very, very helpful. So let me go ahead and hide that, and let's go into router configuration mode. I have OSPF already running. Do show IP OSPF interface. Let's do show IP protocols. And it's not giving me context-sensitive help because I'm in configuration mode. Oh, 10. Okay, so this network statement right here of 10.0.0.0 with a wildcard mask of 0.0.255.255 is already matching on that interface. And that's because the first 2 octets of our loopback right there, they are 10.0. So he's already included. But I just want to give you one other example of how the wildcard mask can be calculated very quickly for that octet, just taking the block size -1. So if we did a show IP OSPF interface brief, there's Loopback 6783. Who didn't get in there? Hold on a second. Do a show IP interface brief. How about Loopback 777? Let's take a look at him. Show IP interface for Loopback 777. Oh yeah, 19-bit mask. Whoop, whoop, boop, 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 boop. So that's not currently, the reason I'm so happy is that interface is not currently in OSPF because the network statement didn't match. But what we can do is, as a review, we can calculate well, we already did on a /19, we can identify what the block size is, and then basically for the wildcard mask for that network, just say -1 to bring it in. So let's go ahead and do that. I have some notes here as well just to make sure we're going to get our math straight. All right, so remind me if you would, with a /19, which we did as an earlier exercise, what is the block size for a /19? Now we'll start there and then we'll do it together. So what is the block size for a /19? I'll give you a moment as well. So if we were going to do that longhand, we would say, well, the first octet is 8, and then the second octet is 8, that's 16. So we're in the third octet, that's the second, that's the third. And so 16, 17, 18, 19, there's the mask in binary. And this is the third octet, that goes to the fourth octet. Great. And so these values, 1, 2, 4, 8, 16, 32, 64, 128, the block size is 32. Okay, great, awesome. So if we wanted to include that in OSPF, what we could do is take that block size for that, and we're in the third octet, and simply subtract 1. So the wildcard mask would be, we care about the first octet, we care about the second octet, and in the third octet, we don't care about the lower 1, 2, 3, 4, 5 bits. And so we take the block size, 32 minus 1 would be 31. And then we continue on. So our network statement would say something like network, and then the network we want to include, and then we could use this wildcard mask of 31, as I note this down, 31.255. And if we wanted to verify the network for that interface, Loopback 777, we could do that as well. So we'll go ahead and do a, let me get my mouse out here. Show IP route connected. And we're looking for this interface right here. Okay, so here's the network. I'm just going to copy this. So that's the network, 1067.64 is the actual network. Router OSPF 1, network. I'm going to right click and paste. Maybe. There we go. And then our wildcard mask says we care about the first octet matching, we care about the second octet matching, and then for that third octet, the block size is 32. We'll subtract 1 for 31. So we don't care about the remainder bits there, and we don't care about the last octet, and then we tuck all of those into area 0, just like that. If we do a show IP OSPF interface brief, now we've just included that network and its associated, that interface and its associated network into OSPF. So we should be able to ping that. So this IP address right here, 10.67.83, even though it's a loopback interface, because we're advertising it in OSPF, we should be able to go to a client, and let's do a trace out to that address and verify we have full connectivity. Yeah, look at that. So PC4 went to its default gateway at .4, who forwarded it to R2, who then sent it to .1 as the, who did we ping? Hold on a second. Oh, ping 10001. 1067.83.1. Who owns that? Oh, and because R1 owns that address, that's R1's external interface where he replied basically that that he received it. All right, I just want to verify connectivity through the network. So let's do a quick spot check and make sure I got all the pieces I wanted to for this Subnet Saturday as I drop my pen. All right, here we go. What is it? What is a block size? It is the value of the least significant bit in the mask. So wherever that shows up, might be somewhere in the first octet or the second octet or the third octet, but wherever that shows up, that's the value, the least significant bit that's on, that is going to be the block size. How do you find it? You take that octet and you put it in binary, you line it up for the powers of 2, and then you put a square around it saying, boom, this is the bit that's on, its value is 32, or its value is 4, or its value is 1 in the case of our first example. And then you circle it. And then you can use it in lots of ways. You can use it to calculate, hey, what are my subnets that I could create, my smaller streets that I could create. You can take the major network, the first one, and then in that appropriate octet, you just add the block size, and add the block size, and add the block size, and add the block size until you're out of IP address ranges, then you're done. That's also helpful to then calculate, if you see an IP address, which network does that live in? You just basically take one network, and then the next one you say, well, this one starts at .1 and it's going to end at .7 because the next one starts at .8, and that's the range for that IP address. So that's helpful in that way. It's also helpful in calculating the wildcard bits. So if you need to calculate a wildcard mask for a certain octet, if you know the block size is 32, the wildcard mask is going to be 31. If the block size is 4, the wildcard mask is going to be a 3. And that's how you can calculate the wildcard mask for it. Yeah, those are some benefits and why it's useful for those reasons. So what we get to do going forward is, and I encourage everybody who's participating and enjoying the stream together, is if you haven't been through the entire, there's only 4 or 5 so far before this, in these Subnet Saturdays, I would strongly encourage you to go through them in order, and that way you'll have all the foundation pieces so we can appreciate going forward how to start getting into custom subnetting. Because, okay, we can take a street, like a big street, like the 10 network, and chop it up into smaller streets. But we haven't really talked about how to do that yet, or like, what should the masks be? Those are all valid questions, spot on, that we are going to answer and solve as we get into how to determine what the appropriate mask should be. I've got some great techniques coming up regarding fingers that you can use without having to get into the binary to calculate what the proper masks should be. And it's a lot of fun. So once you stick with me in this journey through the world of subnetting, because it's a very useful skill. I probably use subnetting to some element almost every time I teach anything regarding IP. Like if I want to create loopbacks, or if I want to configure something on a device, a router, check this out, a router doesn't appreciate having 2 interfaces in the same network. In fact, it won't let you do it. So if we go to R1 and we go to, let's go into configuration mode. Interface, let's go to interface loopback 99. So it's just another virtual interface. No, doesn't cost anything and doesn't really have access to anything, and nobody else knows about it unless you advertise it in a routing protocol. So here's loopback 99. We'll do IP address 10.0.0. Let's see here. How about 12 with a 255.255.248? And it says there's not enough octets here. Hold on. 255. There we go. And that's saying, hey, you can't do that because it overlaps with another interface. And that's basically the router saying, I want 1 network per interface. And what you're saying here is that you have 2 interfaces connected to the same street. And it does that very quickly. But for us, because earlier we calculated the subnets, the 10.0.0 subnet with a block size of 8 because of the mask. And then the next subnet was 10.0.0.8 and then 10.0.0.16. So this address that we just tried to put on there is in the same network, the same 10.0.0.8 network as the other interface. If we used a different IP address, like say something higher than the next subnet 16. So if we used a 17 here, how come it likes that? It likes that because, hey, this is a different network. This is the 10.0.0.16 network that it just added an IP address to. So that's another way to verify that you've got unique subnets. And so now if we did a do show IP route connected, it would show us that it believes it's directly connected to the 10.0.0.8 network and is directly connected to the 10.0.0.16 network. And the block size is very, very handy in calculating what those networks are. So as we continue, that skill of identifying the block size is going to be very, very important. And I have some homework I'd like to do assign you. And then after the homework, I will do some music to close out the live stream. But if you'd like, stick around, and I'd be happy to stick around for 15 or 20 minutes and take your live questions. Now that part will be pruned off of the actual video that's recorded and stored up on YouTube. But I want to do it for you because you're here and I appreciate it. All right, so what was I going to do? Something really cool. I totally forgot what I was going to do. I got excited about the chat afterwards. Because what was I about to demonstrate or do? I think it was going to be valuable. So I think it's good enough to wait for just a moment. And if you could remind me what that was. Gosh. Yeah, I'll take any. Let's see. I was doing. We have our routes. Gosh, I was about to do something really great and I totally forgot what it was. All right. Okay, well, whatever it was, I'm sure it was going to be freaking amazing. But we'll save it for another time. Probably right after the live stream, I'll think, oh, is this I wanted to show them, or I'll listen back to it and I'll remember. Okay, so our objectives that we've covered in this video are, let me go ahead and go right here. The objectives that we covered in this video were, what is the block size, how to calculate what it is, and then I give you 2 or 3 options of how we'll use it in the future going forward. So stick around for Q&A. I appreciate everybody being here. Also, if you have other questions, because when I trim the videos, the actual stream of Q&A that's happening live doesn't get kept or doesn't persist. So if you have a question you'd like me to answer or address, please feel free to add it to the comments for an existing video, including this one once it gets posted. And that way I spend a couple hours a week going through there and making sure I answer all those questions, or at least look at all those questions and answer the ones that I can. All right, so thanks everybody, and I'll see you in the next stream. The next stream is on QoS, so I look forward to seeing you for that, and have a great, great rest of your day. Thanks everybody.
What you're putting in, all your hopes are never